We've been talking a lot about random variables, so let's go back and put that together with something we talked about in the previous week's content. So just recall a binomial random variable, which we could call x because it's a random variable, is the number of successes in n independent trials where p is the probability of success in each trial. So an example of this, let's say a lot of computer games involve random drops, where certain events have a random chance to give items. So maybe you're playing a mining game where each rock you smash has a 14% chance to contain a ruby, and you're going to smash 12 rocks. So you have a fixed number of trials, n equals 12. Each one independently has a 14% chance to contain a ruby. So then x is the number of rubies found in 12 rock smashings. That would be a binomial random variable. And so we can come up with a probability model for x, the number of rubies you could find. Well, you could find 0 if you're really unlucky. You don't find any of them in any of these rocks, or 1 or 2 or 3 or 4, all the way up to 12. Now, you're very unlikely to find 12 rubies in 12 rocks because the probability was only 14% for each rock individually. But we can create a probability model using this command binom.dis.range. The first argument was 12 trials. The next one is 0.14 chance of success. And then the value x or k or whatever you're calling it is just this number here. So you come up with this probability model basically just by copying this down. And we saw this in GeoGebra as well. It'll automatically generate that for us. But the reason I put it here is because now we can treat this like a random variable like we did before, and we can calculate the expected value, variance, and standard deviation. The expected value is the average number of rubies found in 12 rocks. And to find that, you could do this sum product formula with the number of rubies and the probability and get that the average is 1.68. Again, it's an average. You can't really find 1.68 rubies. It would just be if you did this over and over and over again, these 12 rocks, 12 rocks, 12 rocks, and just averaged all those values. And then similarly, the variance and standard deviation we can calculate. We need to do the x minus mu squared times p of x to get that started. And then you do this like we've done before. X minus mu is 1.68 squared times the probability. And you can do this, then you can copy this formula down. And then the variance you get just by adding all of those up. And the standard deviation you get by square rooting that. So that gives you the expected value and standard deviation of a binomial random variable. But the interesting thing is that this is a lot of work, but it turns out that we have shortcut formulas for mu and sigma for a binomial random variable. So the expected value, mu, you can get just by doing the formula n times p. And you can get the standard deviation. Well, you get the variance would be equal, not equals, n times p times 1 minus p, which is similar but different, and it's not really related that they happen to be similar. They come from very different calculations. But the standard deviation, or sigma, if we call it that, is just the square root of that. So it's the square root, dang, bad habit, huh? Square root of n times p times 1 minus p, like that. So if you're dealing with a binomial random variable, you don't have to go through this long process of the sum product here and calculating the variance this way. You can just go ahead and use these formulas. Like if we just do n times p, n is 12, p is 0.14, we get that 1.68. Variance, we just do n, 12 times 0.14 times 1 minus 0.14, which is 0.86 if you're good at that kind of stuff. But if not, just throw it in the formula. And you get 1.4448, like here. Sigma, you just take the square root of the variance, and you get that number there. So if you're dealing with a binomial random variable, you don't need to go through this whole process of making the probability model and using the formulas. You can just go straight to the shortcut formulas, which is very useful when we start dealing with larger populations and binomials that are in the hundreds or thousands.